So for today, we're assuming normal incidence. Which means that the propagation vector is perpendicular to the interface. That'll be Ki for the incident wave propagation vector. This whole problem starts because we have an incident electric field, EI, or really an incident plane wave that has an associated electric and magnetic field. So I'm going to draw EI in the plane of your screen. Here's my incident propagation vector. Now I need to have E cross H point in the direction of propagation, which means that for this wave, H is out of the screen. So that's my incident magnetic field. And we know that EI over HI, the amplitudes of those vectors, is equal to eta 1. We are also going to define, like I kind of foreshadowed in that table, a transmitted wave. So we're going to have a KT, and it's going to have a transmitted electric field that points in the same direction, a transmitted magnetic field that also points in the same direction, and we're going to have a reflected wave. So reflected wave number, Kr, has the same length as Ki because they're both in the same medium, so the wave number magnitude is the same there, but they're going in opposite directions. We define the electric field vector to be pointing in the same direction as Er, but that means, by the right-hand rule, that the reflected magnetic field is pointing into your screen, Hr. So once again, the voltages, that is the electric fields, are going to sum, and the currents, that is the magnetic fields, are going to subtract on this side. So let's write down what this looks like. EI, I'm going to define a direction of propagation. So that's my z-axis right there. And I'm going to say that x is that one, which means that y is out of the board. Out of the board is a dot, not an X. So if I define EI to be x hat times some amplitude EI, e to the minus j k1z. In medium 1, the total electric field that I have is going to be the sum of that and ER, which is x hat ER e to the plus j k1z. And this is the reflected plane wave. So E1 in medium 1 is EI, which is a function of z, plus ER, which is also a function of z. In medium 2, we only have the transmitted wave. So E2 is ET of z, which is equal to x hat ET e to the minus j k2z. Remember that k1 is omega square root of epsilon 1 mu 1, and k2 is omega square root of epsilon 2 mu 2. Now, for the most part, these sorts of reflection at interface problems almost always happen with dielectrics or with good conductors. So it's rare to consider anything where the magnetic constant matters. The permeability isn't usually important in this kind of a problem, but sometimes it is. So we're carrying it around so you know that it's there and where it would pop up, but usually only the epsilons are going to have an effect here. So since the incident and reflected and transmitted waves are all uniform plane waves, we can find all the magnetic fields for any of the magnetic fields by taking the cross product of the propagation vector with the electric field and then dividing it by eta. This isn't the total propagation vector, this is the propagation unit vector. So same direction, unit magnitude. Now we have to talk about what actually happens at the boundary. What are the relationships between these electric fields and these magnetic fields and on either side of the boundary and in each of the media? We have a number of things that have to be true. We know, for one, that in medium 1, EI over HI has to equal eta 1, and so does ER over HR. And in medium 2, we have to have ET over HT equal eta 2. That's not quite enough to solve the problem. We also know some boundary conditions. That is, at the interface between these two materials, the tangential components of the electric fields have to be equal. Mathematically, that's written this way. So the surface normal vector crossed with E2 minus E1 has to equal 0. The tangential components of the electric fields have to be equal, and the tangential components of these magnetic fields have to be equal. The second boundary condition that applies is that the tangential components of the magnetic fields, if you subtract them, their difference has to be equal to the surface current at the interface. Which, unless you're working with a good conductor, doesn't exist. Or I guess if you had some impressed surface current source at the boundary. But for right now, we don't have that, so that's also going to be equal to 0. Under those conditions, here's the situation that we have. These are our boundary conditions, and these are the relationships that we have to maintain between the electric and magnetic fields. Now, because we're at normal incidence, the surface normal vector crossed with any of these field components is just equal to the magnitude of that field component, because for uniform plane waves, the electric and magnetic fields are perpendicular to the propagation vector. So the surface normal vector being also the same direction as propagation vector means that all of these cross products are between perpendicular vectors, which means we just get the magnitudes. So what that means is we can rewrite these boundary conditions as E2, which is actually just the transmitted wave, minus EI plus ER, because that's the field in medium 1, which is the incident and reflected wave. And those have to equal 0. And then the second boundary condition becomes HT minus HI minus HR, because remember, these two vectors are in opposite directions. And that has to equal 0. Now we're going to define the reflection coefficient. And just like for the transmission line problem, we're going to say that the reflected electric field is equal to the reflection coefficient times the incident electric field. And we're going to say that the transmitted electric field is equal to the transmission coefficient times the incident electric field. Based on that and our intrinsic impedances for the two media, we can simplify those equations further, and then we get T minus 1 plus gamma all times the incident electric field equals 0. And then we get T over eta 2 minus 1 minus gamma over eta 1 all times the incident electric field is equal to 0. Canceling out the electric field by just dividing through on either side, we end up with the result that the transmission coefficient is 1 plus the reflection coefficient. So far, so good. And then on the other hand, we have that transmission coefficient, so 1 plus gamma over eta 2 minus 1 minus gamma over eta 1 is equal to 0. Multiplying all this stuff out, we get eta 1 plus gamma eta 1 equals eta 2 minus gamma eta 2. Move some things around, we end up with gamma times eta 1 plus eta 2 equals eta 2 minus eta 1. So gamma equals eta 2 minus eta 1 over eta 2 plus eta 1. There's our reflection coefficient. If you remember, the reflection coefficient for transmission lines is the load impedance minus the characteristic impedance divided by the load impedance plus the characteristic impedance. I suddenly can't write a Z. It's Friday. There we go. So for transmission lines and plane waves, the parallels are clear. The intrinsic impedance of medium 1 is serving as the characteristic impedance here because that's the one that is governing the electric to magnetic field relationship of the incident wave. And then eta 2 and ZL are both the new relationship that governs the boundary. And then when the wave hits the boundary, that relationship needs to be satisfied. So that's why eta 2 and ZL are parallels here. We're going to do a couple of simple sort of brain exercises about this type of problem. Oh, and I got to tell you one more thing before I do that, and that is that since the transmission coefficient is equal to 1 plus gamma, that means it's equal to eta 2 plus eta 1 divided by eta 2 plus eta 1 plus eta 2 minus eta 1 over eta 2 plus eta 1, which works out to be 2 eta 2 over eta 2 plus eta 1.